All right, class, today we are going to review identifying types of chemical reactions and predicting products. This is largely a review of what you learned in sophomore chemistry. And we will be covering sections 4.1 and 4.7 in Unit 4. So if you see here on the slide, we are going to be looking at essentially 6 different types of chemical reactions. Combustion, synthesis, sometimes called combination, decomposition, single displacement, sometimes called single replacement, double displacement, sometimes called double replacement, exchange, or metathesis reactions. And those can kind of be broken down into 2 types, precipitation and neutralization reactions. And then finally, we'll be looking at oxidation reduction reactions. Now, oxidation reduction reactions, basically combustion, synthesis, decomposition, and single displacement reactions are a form of oxidation reduction reaction. So that category kind of covers multiple of the other categories that you see above. Now, we're going to take each one of these types of reactions and talk about how would you recognize a type of reaction as a combustion reaction, as a synthesis reaction, etc. And once you do that, what are the tips for predicting the products of that type of chemical reaction? So here we go with combustion reactions. The combustion reaction is defined as the reaction of a hydrocarbon or carbohydrate with oxygen in which heat is released. These are all exothermic, by the way. And how would that look like? How would that appear? On the reactant side, you would see a hydrocarbon or a carbohydrate, something that contains CH and O, or something that just contains C and H. The other reactant will be oxygen. Now, these are the easiest type of reaction to predict the products of. The products of combustion are always CO2 and H2O. So for C4H8 plus oxygen, CO2 and H2O. For CH2O plus oxygen, CO2 and H2O. Now this may not look right because there's a lot of carbons there's a lot more hydrogens than are present, but remember, the way you deal with that is you would balance the chemical equation, which we're going to do here in a second. But for combustion reactions, always CO2 and H2O. So you see I balanced the reaction of C4H8, and then we'll do C2HO. So there's one carbon. There's this oxygen here, and this, I think actually this one is balanced as written. So this one would have coefficients of 1 to 1 to 1 to 1. So that was combustion reactions. Now we'll talk about synthesis. A synthesis reaction is when a single compound forms from 2 or more reactants. So on the reactant side, you have 2 or more species, 2 or more elements or compounds. On the product side, you would have 1. So if on the reactant side you have 2 elements, so for example magnesium and oxygen or calcium and chlorine, if they're going to make one product, essentially those 2 are just going to combine. So how would you predict the product? Well, for that you have to kind of see who's reacting. Magnesium is a metal and oxygen is a nonmetal. If they bond, they would form an ionic compound. Okay. And then when you go to write the formula for this ionic compound, well, you have to write the ions, and then you have to balance the charges between those ions. So what are the 2 ions here? Well, the 2 ions would be magnesium, which is in group 2, so it's a 2+. Oxygen is in group 16. It would make a 2- ion. And to balance those charges, 1 magnesium would bond to 1 oxygen. So that would be your products. Well, then we would balance it, and to balance it, you just need to do that. Let's look at the reaction with calcium and chlorine. Again, we have a metal bonding to a nonmetal. So we would then, all right, we have to write the ions. So your calcium ion is, again, that's in group 2. So it's a 2 plus ion. Chlorine is in group 17. It would make a 1 minus ion. To balance those charges, you would have to have 1 calcium bond to 2 chloride ions, and there you have your answer. This one also is balanced as written. Now, sometimes you have 2 compounds combining to create 1 compound. In that case, that's still a synthesis reaction, although these would be a little trickier to try to predict the products of. So in general, you're going to just be asked to predict the products of a synthesis reaction when 2 elements combine, not 2 compounds. Okay, moving on. Decomposition. Well, decomposition is really the opposite of synthesis. On the reactant side, you have 1 compound. On the product side, you'll have 2 or more products. So we'll go with calcium chloride. So again, to predict the products of decomposition. Well, here, this is what we call a binary compound, which that means it's just composed of 2 elements, calcium and chlorine. Same here. HF is also a binary compound. Baking soda, NaHCO3, has actually 4 different elements in it. It's not binary. It would be called ternary. Also, we can also add something like potassium nitrate decomposing. This would be called a ternary compound because it has 3 different elements in it. So that's a little sidelight kind of that terminology. Bottom line, though, is when you're doing a decomposition and you're asked to predict products, we're going to stick with the binary compounds. Because when the binary compounds decompose, they are most likely going to decompose into their 2 elements. It's a little bit trickier to predict the products of, for example, NaHCO3 or KNO3, what those would break up into. You would still be asked to recognize that this would be a decomposition reaction because it has a single reactant, but you wouldn't be asked to predict the products. So now let's go back up, and if calcium and chlorine were to decompose, calcium chloride, it's going to make calcium the element and chlorine the element. Now, chlorine is one of the Brinkelhoff elements. If you recall, there are the series of elements that Brin, Cl, H, O, and F. These guys are so reactive that if they're not bonded to someone else, like they are here in calcium chloride, as an element, that atom will bond to itself to make a diatomic element. A diatomic element. Now remember, diatomic means it's composed of 2 atoms, and the bromine, iodine, nitrogen, chlorine, hydrogen, oxygen, fluorine are the 7 diatomic elements. They occur in nature bonded to themselves. So when you write the elemental form of chlorine, you would write Cl2. Okay, how about the decomposition of HF? So let's do that one. Well, that's going to break up into hydrogen and fluorine. So hydrogen is one of the Brinkelhoff elements. Fluorine is also one of the Brinkelhoff elements. And so that's how you would write it. That would be the products. And of course, the first reaction is balanced as written. This one here, we would need to put a 2 here. And the thing is, I'm balancing these because really once you predict products, you should really always balance your chemical equation. Okay, we're going to move on to single displacement here. Single displacement, again, sometimes called single replacement. It's when a lone element reacts with a compound. And what's going to happen is the lone element is going to react with the compound and create a different lone element and a new compound. And the single displacement reactions are a little different depending on whether the lone element is a metal, as it is with aluminum, or a non-metal, as it is in the second reaction, where the lone element is chlorine. There should be a plus sign here. Okay. All right, back to it. So aluminum is a metal. And in a single displacement reaction, what happens is the aluminum, the metal, will displace the metal from the compound. And so the first product, the new lone element, will be the metal that was bonded. So in this case, copper. The other product will be when aluminum then bonds to chlorine. Well, aluminum is a metal, chlorine is a nonmetal, so you would have to write the ions off to the side here. Aluminum is a 3+ ion. Chloride would make a -1 ion, and they would bond in a 1:3 ratio. So you're making an ionic compound there. And so this would be your products of the first reaction there. Okay, I went ahead and balanced that offline. So let's look at the second one there. So we have chlorine, the element, reacting with potassium bromide. In this case, the nonmetal will displace the nonmetal from the compound. So the new lone element is going to be bromine. Well, bromine is one of the Brinkelhoff elements, so when we write its formula as an element, we need to write Br2. And then that leaves potassium to bond with the chlorine. Well, so then that's an ionic compound because it's a metal with a charge of +1, and chlorine with a charge of -1, that ion. So that would be KCl. They would bond in a 1:1 ratio. And again, to balance this, you would need to put a 2 here and put a 2 here. So that's single displacement. Here we go. Let's continue. Double displacement or double replacement. It's when a gas, precipitate, or covalent compound forms from the apparent exchange of atoms. Okay, it looks like things are going to swap who they're bonded to. An apparent exchange of atoms or ions between two compounds. All right. So then on the reactant side, you will see two compounds. Very often those are ionic, not always. On the product side, you'll get two new compounds. Now, double displacement reactions kind of get split up into two different kinds of double displacement. First one, so let's look at precipitation first. It is a double displacement reaction in which a solid forms from the exchange of ions. And so usually the way this is set up, you have two ionic compounds dissolved in water, so those are aqueous solutions. They're going to react. Well, to predict the products of a double displacement reaction, generally what happens is the ions swap partners. So silver ion would then bond to chloride ion, and potassium ion bonds to nitrate ion. And so to write those products, because they're ionic, you would write the ions and balance the charges. Let's look at KNO3 first. So we're going to look at KNO3. We're going to write K+. NO3 is nitrate. It's a -1. So they're going to bond in a 1:1 ratio. That silver ion, because it's bonded to nitrate, is a +1 ion. Chloride would form a -1 ion. And again, silver chloride would be AgCl. Now, which one of these guys would be the solid? Well, for that, you would need to refer to the solubility chart. And that'll be always given to you, but it turns out in this case, chlorides, compounds that contain chlorides, are usually soluble, but not when they're bonded to silver. So this guy would be the solid. And again, you would have a solubility chart if you had to predict this. Now look at the other product, potassium nitrate. All compounds containing nitrates are soluble. That's the general rule. And so this would be aqueous. Okay, we're going to do many more of these as we go on, but this is just to give you a flavor for how you would determine the solubility of the product here, which one would be the solid that forms from the exchange of ions. Okay, let's move on to acid-base neutralization. Well, an acid-base neutralization is when an acid reacts with a base. Now, how do you know it's an acid? Well, one of the definitions of acids is that they contain hydrogen ion or ionizable hydrogen. So HCl, when that dissolves in water, if this would be aqueous, If this would be aqueous, it would dissolve into hydrogen ion and chloride ion, and sodium hydroxide is a base. Well, the simplest definition of a base is a compound that contains hydroxide ion. Again, this would just be dissolved in water, and it would dissolve and it would be aqueous. So kind of looking at this, so that's why the general description up above says an acid is HA, where A would be whatever this anion is. In this case, it's chloride ion. And then BOH. So B would be whatever the metal or whatever the ion is that's bonded to the hydroxide ion. And what ends up happening is it creates water. So there's still a swap. There's still an apparent exchange of bonding partners. So H would go with OH. That's where you get your water. And then Na would go with Cl, and that's where you get your salt. So essentially the positive ion from the base would react with the negative ion, the anion from the acid. So in this case, we would get H2O, water, and sodium would bond to chloride. We know that's NaCl because that's a +1 ion and a -1 ion. So that's pretty much it for acid-base neutralization. Finally, let's look at oxidation reduction. As I mentioned earlier, the oxidation reduction reactions can be synthesis, single displacement, decomposition, or combustion reactions. The only type of reaction that is typically not an oxidation reduction reaction are double displacement reactions. What is a redox reaction? It's a reaction in which electrons are exchanged by reactants, and the charges of some reactants are changed during the reaction. Now, we're going to learn more about this later, but just now we just want to be able to recognize it. So if you have a synthesis reaction, a single displacement, a decomposition, or a combustion reaction, then those would be considered redox reactions. But we'll at least look at this first one here. Sodium is an element in this case. And so elements, as we'll learn in a few classes, well, elements are neutral. So sodium here has a charge of 0. Well, chlorine is an element. It would be considered to have an overall charge of 0. But we know that in sodium chloride, sodium forms an ion. So here, sodium is a +1, and chloride is a -1. So if you kind of see what happened here, sodium lost an electron to become sodium ion, and chlorine is gaining an electron to become chloride ion. And we're not balanced here, and that's okay. We'll put a 2 there and a 2 there, but you get the general idea that sodium has changed its charge. Chlorine has changed its charge. Here we go. Next one, aluminum. Again, an element, no charge. Here, this is copper 2 ion. So this here, copper is a 2+, and chlorine's a 1-, or -1. Let's look at the charges on the product side. Well, we said aluminum forms an ion, so here aluminum would be a 3+ ion. And chloride 1-. You can just write it like that. Copper, copper is an element now. That's going to have a charge of 0. So again, how do we see the charges change? Well, copper went from being a 2+ ion to being an element with a charge of 0. Aluminum went from being an element with a charge of 0 to a charge of 3+. So hopefully you can see how there is this exchange of electrons between these guys, and different species are changing charge. Now to wrap this up though, let's look at the type of reaction that is typically not a redox reaction. I said a double displacement reaction is typically not. So let's look at this one. Well, in this case, sodium is bonded to bromide ion. So sodium's an ion, so it's a +1. Bromide's a -1. Here, the lead ion is lead 2+. Nitrate, well, the whole ion is -1. There's 2 of them, but still -1. Okay, let's look on the product side. Well, here, lead, it's bonded to 2 bromides. Oh yeah, these guys did their swap, right? The apparent exchange of bonding partners. So lead, lead's still a 2 plus. This is bromide ion. It's still a 1 minus. Sodium, yeah, sodium nitrate. Well, sodium is an ion here, so it's also a plus 1. Nitrate is still, that whole ion is a minus 1. Did anybody change charge? No. Sodium was plus 1, it's still plus 1. Bromide was minus 1, it's still minus 1. Lead is 2 plus, it's 2 plus. And nitrate was a 1 minus, and nitrate is still a 1 minus on the product side. So here you go, double displacement, yes, not a redox reaction. All right, that about wraps it up. 20 minutes. There you go.